So here's the whole switch sensor board. It's fairly small, as can be seen next to a 1 cent piece. Quick overview of the components: the power in positive, power in negative, switched negative output and positive output. Positive output is electrically the same as the positive input. So we're actually, with this board, switching the ground side of the load. Load could be a set of LEDs, like in this case direct driven LEDs, upside down so we don't blind the camera and ourselves. This board has several components on it. There's a voltage regulator to provide power to the Hall sensor switch, which is this device here. This is the regulator. This is an inverting device. It's just a FET to invert the sense of the output, so that we normally, with no magnetic field, have this board off. As can be seen, there's no light output right now. This is the power FET. The electrical path goes through the FET when it's switched by the rest of the circuitry. The board is single-sided. There are no components on the bottom side. The bottom side is totally flat, making it easy to mount to a heatsink or to the body of the light for lower power situations where no heat's generated. So let's do some quick demonstrations here. I'll bring a magnet across here. This is a small magnet. If I bring the magnet near the top of the sensor, we're switching the load. You can see the load is roughly 4.9 amps, nominally 5 amps from the power supply. The clicking you're hearing is the power supply coming out of constant current regulation. Obviously there's no moving parts on this board itself. The magnetic field has to be applied the correct direction, so if you flip the magnet, bring it down, it doesn't activate. Flip it over, bring it down, it activates. The board is fairly sensitive. It could be activated through the board, in fact through the board and through the housing. So if we take our magnet and leave it in this orientation, push the magnet underneath, you can see it's activating. It's a 1/4 inch piece of bar, aluminium bar. I can put it over the magnet, bring down the sensor, and still see it's happily switching and still from quite a distance above the board. This is 1/2 inch aluminium stock. Place it this way so there's no slots in the way, and you can see it still easily activates. So there'd be no problems whatsoever mounting this board to a bar this thick, say a very heavy duty dive light, and still easily be able to activate it from a magnet on the other side of the housing. Supplied with the board to make it easy to attach will be a piece cut, then you can do the final trimming. This is thermal pad material from Bergquist. It's a double-sided insulator. It has adhesive both sides. You peel both sides away, peel one side first, clean the heatsink, mount it down. Heatsink can obviously be the body of the light itself. Mount it down, then peel off the other layer, mount the board down onto it, apply pressure. It'll feel like it's not sticking that well. This is an acrylic based adhesive that they're using, which takes upwards of 24 hours to fully set. Once you apply it, it's recommended to apply pressure. The datasheet gives some recommended values. We don't really need the thermal capability that much in this design, so this is really being used more to just hold the board down. But some heat is being dissipated by the FET, even though it is a 0.006 ohm or 6 milliohm FET when it's turned on. Give you an idea, we've had it running for a little bit. This is ambient temperature in the room at this time, and if I measure around on the board, you can see that it's reaching upwards of 29 degrees centigrade. So it is warming up, not particularly quickly, So any kind of housing will easily keep this board cool, and this board right now is running close to 5 amps. It's conservatively rated at 10 amp drive. It could go above that, but I tend to rate most of my designs on the conservative side. And you can see it's scan around, it's probably just about reached steady state. You might be able to hear the fan on the power supply. It's increased revolutions as we've been doing this test. It's putting out close to 18 watts, and so the power supply has kicked the fan up to a higher speed to keep itself cool. And this board here is, yeah, we've got to maybe 31 degrees, 32 degrees. Still nice and cool. Can easily put my finger underneath. I'm not screaming in pain. Magnetic field is going through my hand, so you're getting an idea again just how sensitive this whole sensor is on this board. So I hope you like the demonstration.